the recording of the previous lesson. If I didn't, I'll go back and do it. But similar triangles. Now, these were the requests from homework. So what is this? 2Q. Was it 2Q? 3Q from the old textbook. We're live. Now, question 1B. Great. I didn't want to ruin your fun for this one, but the challenge is, how many triangles do you see here?
3.
Yes, 3, they said. Because in the previous questions that we've had, we've actually only had 2, dos, right? And have we got all 3 similar triangles? We have actually. People said no, but we do. So if we look at this, we can see that clearly we've got a 90 degree here, which means that's 90 degrees also. Yes? If we look at the little triangle, let's call this angle alpha. Well, medium triangle, I should say. The medium triangle. Now, if that's alpha and this is 90, what must this angle here be? 90 minus alpha, because there's 180 degrees in a triangle. If I look at the bigger triangle, I've got 90 there. I've got alpha here. So wouldn't this angle here have to be 90 minus alpha? Oops, that's a minus there. Yeah? And if that's 90 minus alpha and that's 90, wouldn't that have to be alpha? So we have got 3 triangles that are equiangular there. Which triangles do we have to use, or should we use? Well, if I went for the big triangle, I'm going to be a bit stuffed. Why? I've only got one piece of information. I don't need the others. So I'm actually going to look at the 2 smaller triangles. Now, normally I say draw the triangles separately, but quite frankly, they are drawn separately, just side by side. So I'm going to start with my unknown. So I'm going to go x over 3. And this is where it's really important that you find the matchy-matchy. So this x here on the medium-sized triangle is 90 to 90 take alpha. Do you agree? So what's its buddy on the right-hand side? Yeah, 90 to 90 take alpha. If you said it was x again, you're going to be stuffed. Right? So over 2 and 3, 90 to alpha. 90 to alpha here is x. So we cross multiply, we get x squared equals 6, and therefore x is root 6. We don't even entertain the possibility of a negative value there. Yep. Dev, you put your hand up before. Yep. Question C is great. And this is one where the triangles have been rotated. So again, you can't just go matchy-matchy. I would strongly recommend draw the triangles separately. It just means you have to do less thinking. Your brain doesn't have to work as hard. But when you do this, please make sure you label your angles. So we've got, if I'm looking at the bigger triangle, that's beta. And by the way, why are those triangles similar? You've got one given and this common angle here. Okay? So I must put that in there. So the bigger triangle, what are my lengths? What's this whole length? Yep, x plus 7. What's this length? X plus 2. X take 3 plus 5 is x plus 2. And then the little triangle, again, make sure, like it fascinates me, I've got students who label the triangles and everything, but they don't put the angles in. So how do you then know which side corresponds with which one? Because when they do it like this and they don't put the angles in, guess what they do? They say this side corresponds with this one, and that's just not possible, is it? So anyway, what have we got? That's 7, and this is x take 3. So we start with our unknown. Oh, geez, we've got 2. So just it's on top, so I'm going to go x plus 7 over x plus 2. Equals, now x plus 7 is blank to dot. What is blank to dot over here? X take 3. But do you see how some people would stuff it up and they've just gone, yeah, that one and that one is the same? And it's not. Okay, and x plus 2 is beta to dot Beta to dot is 7. At this point, I'd like to think we're pretty good to solve. We just cross multiply. So we've got 7x plus 49. We're going to multiply these out. So it's x plus 2 times x take 3. So it's x squared take x take 6. All right, if you want to put in an extra step there with the brackets, please do so. I'm just speeding it up now because I've got people tuning out. So I've got x squared take 8x take 55, and what would I do? To the calculator. Well done. Solve it. I ignore any negative value and I pop it in. Even if I had let's say I had a positive value of 2, could I accept 2 as a solution? No. Why? Right, because 2 take 3 will still give you a negative answer. So don't just go, oh, it's still a positive, that's okay. Check it by substituting back into the question to see if they're both viable solutions. Is that okay? Yep? Let's ask. Right, if we had, I don't know, let's go beta, alpha, and I said 10, and then I've got beta, alpha, and I said 10. I've got 2 angles that are the same and a side that's the same. Huzzah! Negatory. This is not. It is not as, because this is opposite your alpha and this one is opposite the beta. For it to be congruent because of as, then you've got to make sure that they're opposite the same angle. All right? So, if you did not do it, I strongly recommend that you go through. This is just looking, sussing. Is it congruent because of whatever rule? Is it not enough information to prove congruency? I'm not going to ask you to do it now because we don't have time. I want to focus more on, because that's just a look, see if you're right or wrong, and then understand why. We want to actually apply and do a little bit of a proofy thing again and show you how you write these proofs up. Okay? Remember, the whole point of this topic is circle geometry, and within circles you might have congruent triangles or similar triangles. God forbid. So here we go. Explain why ABC and EDC are congruent. So we look at it. What's the first thing that we notice? Or you notice? Well, first thing I notice is the parallel. We've got parallel lines. So straight away, I'm going, right, congruence. Not congruence. I'm going corresponding. What was the C word? Corresponding, alternate, or sure. Co-interior. Thank you. That's what I was searching for. Good lad. All right. So what do we notice? We've got parallel lines, and I can see straight away 2 vertically opposite, and I've got a side and a side. So a simple way, if you can't find this, if you ever get stuck, so can we rule out RHS? Because we don't have a right angle. I've got one length, one side, so all the S's are there, yep, and I've got one angle. Is it possible that I can show another side is the same? Really? Where have I got another side length is the same? Why? We've got one side, I've already counted that. Have I got another pair of lengths that are the same? Would AC and CE, because they're parallel? No. They look they're the same, and we'll eventually prove, but we can't say they are. So that's actually ruled out, and that's ruled out. It has to come down to AAS, and that is because we've got parallel lines here, and that means this angle is the same as that one. Okay, check. Is the length that I have opposite the blank, correct? So these guys are congruent because of as. So here we go. How do we write it up? We're going to say BC That's the length. Length, right? Absolute value sign, modulus. The length of BC equals the length of CD. How did we know that? Given. We know that angle BCA equals, no, angle BCA. So this angle equals DCE. Why? Vertically opposite. Now we're doing the parallel line bizzo. So angle ABC is equal to CDE, and why? Cannot just say parallel lines, right? So in this case, it's like the alternate, there we go. So therefore, triangle ABC. Now, watch this one. 1, 2, 3. It's congruent. Now, people who are really particular, they'll do the angle, the lengths in the same thing. So ABC, I'd go DEC. I don't really care, but I'm still going to write that DEC. You could just go CD. Do you know what I mean? So A, B, so I went from, oh, I shouldn't have gone D, I should have gone E, D, anyway, it doesn't matter. And not finished, don't do all the hard work and not finish off by giving the reason, ass. I'll try and come up with questions so you can mumble in the test, ass. The fact that you've just proved they're congruent means that everything, they're exactly the same. These triangles are the same. So that means this angle, this length and this length is the same. It means that this length and this length are the same, and that one and that one are now the same. Okay? So if AC is 6, what is the length of CE? It is also 6. Why? Because they're corresponding. What's the size of angle DEC?
So these aren't just congruent.
This will equal, DEC will equal angle BAC, which equals 42. Get something around. I do want to get to the laser cutter. We should make some circle things. Anyway, O is the center of 2 concentric circles. Now, that is a new word. Someone just asked, what does concentric mean? If you look at the diagram, what do you think it means? Same center. Okay, concentric, they've got the same center but different radius. Archery board, dart board, you've got concentric circles. Right, AB is a diameter. So that means you know it's going all the way through. So because it's diameter, could we straight away go? And that's what we want to start doing too with these diagrams that we have, things that we see, let's put on. And radius is always a great one. If you've got radius going there, put the little dash. Suddenly you see, not in this one, but suddenly you will see isosceles triangles. You will see all sorts of things. So if you know it's radius, dash, dash. All right. Tangents at A and B. Now, do you remember what a tangent is? Okay, it is a straight line, but it's also something that just touches. Okay, it just touches the circle. This thing here, where it cuts the circle, that is what we call a chord. C-H-O-R-D, a chord. But when it's just glancing the circle there, it's just touching. Now, the good news, well, the weird news, is that when we do our circle theorems, what you will discover is when you've got a tangent and a radius, that's 90 degrees. You would have known that from year 10, but we skipped that unit. So you're allowed to assume that. Happy with that? Tangents at A and B are drawn to cut the larger circles at M and N respectively. Prove that AM, ooh, my initials. Prove that AM equals BN. Now we could go, oh my God, it looks like they are. Surely they have to be the same. What would you like to do? Correct. So I said draw a line between A and N, and because, well, N and the origin. Because the first thing someone said was, don't do this one, there's no triangles. Well, let's make triangles. So we're going to draw N to here, and we're going to draw O to M. Ooh, that was bad. Now, do we know that NM is a straight line? We don't know that it is in fact the diameter. It could be a little bit off center. It could be like there and a little bit, I exaggerate, but we can't assume that it's straight across. What we do know though is this O to N is the radius of the big circle, and O to M is the radius of the other circle. Hello.
I reckon we've got plenty of evidence to assume that it's a straight line.
N to M is a straight line?
Yeah.
Why?
Well, because both A to M and B to N are at 90 degrees from the origin.
But we're trying to prove that A, M and B, N are the same length, so you don't know that they're... Because how do you know that that might have been out there a little bit and then it's not a straight line? It wouldn't be going through the origin. Yeah, but this is what you're trying to prove. Anyway, you're just a minor little step away. So why can we say that yes, of course, AM and BN are the same? Because where's the hello? RHS. We've got the right angle is the same. We've got one side is the same, and the hypotenuse is the same. So they are congruent because RHS, and then of course, boom, they're the same. We good? All right, let's move on to and start. Oh no, we're going to do a little bit more geometry. Both of these are really great theorems. So use the diagram to establish the angles of a triangle theorem. What is the theorem for angles of a triangle? They add up to 180, okay? But again, we're going, well, we know that they do. Why can't we just say it? What else do you see there? Parallel lines. How can I use the parallel lines? Pardon? Yep, so if this is A, what else is A? That is A. Why? Alternate angles. And because this is B, that is B, why does that make us then say, haha, A plus B plus C must equal 180 degrees?
We don't know that C to D is
Boom.
parallel.
Hello?
Because the straight line has to be 180.
180 degrees in a straight line, correct. Okay? So we see what's going on? Great. We're now going to do number 2 and we'll write it up. This might be one of my favorite. Is it one of my favorite? Yes, this is one of my favorite theorems for triangles. And helps you, sometimes it helps you save one step of working, but it's quite good. Does anyone know what the exterior angle of a triangle is? Wowza. Good-o. That's good to know. So here we go. Interesting. So we're going to prove it without knowing what it is. So we see the parallel lines. What can we do? Right. So get your little Z thing happening here. So, right. So that's C. That has to be C as well because of alternate angles. Do we agree with that? Okay, so we are going to write this one up. So we're going to say angle CBE equals angle ACB, which is C, and why is that? Alternate. Normally I just write alt. Today I don't know why I'm writing alternate. Okay, anything else? I want to get angle EBD. Yep, why is angle EBD equal to CAB? Corresponding angles. Now, someone else was going to say something else then. Yep. Right, so you could also do that as saying, well, A plus B plus C has to equal 180 degrees because 180 degrees in a triangle. And so I've got B and C. This is a straight line that has to also be A because 180 degrees in a straight line. But you told me corresponding first. But you can see already there are two different ways that we've just come up with in seconds. So big warning. If you're looking at your neighbour's work in a test or even in classwork, it doesn't have to be the same as yours. And very often it is exactly the same. I will be suspicious. So EBD equals CAB. So that's the slide, the corresponding CAB. Corresponding. Okay. Therefore, here comes, we'll better label it. Here is the exterior angles of a triangle theorem, that these two angles added together give you that angle. So if you ever have a triangle, and we can draw it just a different way if you like, if we have that going on there, and we've got, I don't know, 40 and 50, I can say straight away that's 90 degrees there. You could have also found it by going, oh, 180 degrees. So 180, take 50, take 40, get this angle, then 180 degrees, take that one because it's a straight line. Just saves you one step, knowing. Okay? So therefore, angle CBD equals angle CAB plus ACB. That is your exterior angle of a triangle. Okie dokes. But you're getting used to, hopefully, writing down your thinking, in mathematic notation. You good with that? Okay, let us actually start. You like this and I'll be able to shut up now. We're going to start looking at our theorems. I might even be able to go and get you your photocopies. Okay. Just some language that you've already known. Circumference, love it. And arc, you've learned that in methods, right? Arc of a circle. You've got the chord that we just talked about. Semicircle or we can't say hemisphere, but a tangent, it just glances. Sometimes if they've got a worded question, they will refer to the minor arc, which is the shorter distance between B and C. Major arc is the longer one, and so on and so forth. The origin, the center, is normally called O, with a nice big circle around it. So these are the various theorems, and you don't have to write these down because I will give you a little booklet that's got all the relevant theorems, including our parallel line ones, that we will be using. So, boom, 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 boom. What this little section does, the new textbook, it goes through, it'll take the angle and the semicircle, we'll just look at that, and it goes through it all one by one. It's like, no, no, no. I like the old textbook. So, it's a bit of matchy-matchy. Yeah. Okay, I am not going to shut up just yet. Some of these, we are proving those theorems that were just up there. And where I will eventually get to go, yeah, I'm done now, is stuff like this. And it's just solving. And you're using the theorems. Okay? So, first one we'll do together, then we'll do one of those other ones, and you will try and work your way through over the long weekend. Good luck. I know. C is the diameter of a semicircle. Center O. Use this figure and assume properties of isosceles triangles. Oops. Hopefully if I underline. Of isosceles triangles. So it's giving you a bit of a hint, isos, to demonstrate that angle ABC is always a right angle triangle. When I normally used to do this with year 10s, I would come in, give them all compasses, and draw a circle, put a line through the diameter, and then put $100 on the table. And I said, and anyone can have that $100 if they can draw a triangle diameter, 1 point on the edge of the circle, and it's not a right angle. And you should see them. Oh, oof, they go. Measure. It's not possible. This will always be when you've got angles, because this is one of our theorems, right? Angle in a semicircle. Right? That, if you got, it goes through diameter, that angle is always going to be 90 degrees. Right? Made me laugh for a little while. So here we go. Can we prove it? So what's the first thing that we want to do? Radius, radius, radius. Radius, radius. Radius here, radius here, radius here. So what do we see before our magnificent eyes? They even gave us the hint in the question. They gave us the hint in the question. We see isosceles triangles. And so, if you're looking at this, if those two lengths are the same, don't these two angles have to be the same?
Yes.
And if that is B, doesn't that have to also be B?
Yes.
B, 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 B. Right, and guess what? You've pretty much proved it. How? How do you know A plus B is 90?
Because the semicircle rule.
No, we're trying to prove that rule. You can't say A plus B is 90. We're actually trying to prove it. Yeah? There's 180 degrees in a triangle. So 2A plus 2B equals 180. So doesn't it have to be that A plus B equals 90? Let's write it up. Now, very often, you're going to play with the diagram. You're going to go, yeah, I can see. But then the write-up is the issue. So let's get used to that. So where did we start? Right, we said that OA equals OB equals OC. Radii. You can put radius if you like. I don't mind. This led to, so that gives angle OBA equals angle BAO, which is A. Why? Good. Isos triangle. And angle. Which one, sorry? OBC. OBC equals angle OCB, which is B. Why? Isos triangle. Fascinates me that people who want to leave today will be able to show me their book. I try really hard to write slowly. Right, now we said, therefore, 2A plus 2B equals 180 degrees. Why was that? Because there's 180 degrees in a triangle. Try your hardest. And therefore, A plus B equals 90. So, i.e., angle ABC. So find your tab on OneNote and you've got these here. Okay, you can keep these open on your laptop. I'm looking over here. So you're looking at the first one and you're looking at all those theorems and you're going matchy matchy. Which theorem is this? Angle in a semicircle, correct. So as soon as you see this, we should be going, hey, I know that that is 90 degrees. Agreed? And that's what we have to write down. So we will write angle ACB equals 90 degrees. Why is that? Angle in a semicircle.
So now we're allowed to say that. What?
Pretty simple. 180 degrees in a triangle. So therefore, x plus 3x plus 90 equals 180 degrees. 180 degrees in a triangle. You can then find x. Agreed? Would you think, what about B? Basically the same. Excellent. So, what about C? Because my time is done. So, have a look. Look at your theorem, see what one can apply. When you look at this, absolutely, tangent is the key word. You guys have picked it really well. Not going to go through any of these because they don't have the tangent. This one is great. I think that one's going to be helpful. Agreed? What is that telling us? That this is 90 degrees. Do we know anything else? We know what part of it is. Yep, that's 80 take x here. So this angle here would have to be 90 minus 80 take x. So it is 10 plus x. Do we know anything else? RTS is also 90. Why? Angle in the semicircle. Okay, so we have to again write this up. It's well and good. We can now go, yeah, x plus 10 plus x has to equal 90 degrees because there's 180 degrees in a triangle. But just giving me the answer, x is blip, doesn't get you. That would maybe be worth 4 marks. You get 1 out of 4 telling me what x is. It's all the other stuff that gets you. So what did we start with? We started, I might go, angle. I know I didn't start with this, but I'm going with RTS equals 90 degrees. Angle in a semicircle. Do you like my abbreviations now? So that's angle. Right? Angle RSU is also 90 degrees. Angle in a it's not angle in a semicircle. Radius tans, yep. It's getting excited because I can hear people packing up next door. Radius tangent. Right, therefore, angle, you're not packing up, RST equals 90 minus 80 plus x, or put the bracket if you want, so 10 plus x, y, right angle, 90 degrees, whatever you want. Is that chap waiting for someone? Or does he want to see me? Who knows? Therefore, x plus 10 plus x plus 90 equals 180. 180 degrees in a triangle. And away we go. Now, homework. Hate to do it to you, but the rest of the term is going to go a lot smoother if you are trying to work your way through these. I will make an effort to write work solutions for these, but try not to look at it unless you absolutely have to. Okay? So we're trying to finish these. 3E. Yep.
We use it on one page that has